windows that don't get wet, paint that stops fires. New ideas that are possible because of nanotechnology that lets us control atoms and molecules on the nanometer scale. The growing area of nanotechnology raises many health issues related to biosecurity of products. In Belgium, the Walloon region has asked the University of Namur, known for its expertise in nanotoxicity, to study new nanomaterials for any potential hazard. The initiative aims firstly to aid Walloon businesses such as NanoSil, a university spin-off which analyzes the potential human health risk of the technology. Secondly, the project will also develop protocols to test nanoparticle toxicity based on cellular structures. Within the framework of this project, entitled Nanotoxico, the nanoparticles developed by Walloon Industries, such as carbides of titanium and silicon and carbon nanotubes, will be studied. Nanotoxico is a multidisciplinary project bringing together 4 components for the research: classification, in vitro toxicology, health and pharmacology, and lastly, communication. Given their size, nanoparticles have physical and chemical properties that make them potentially hazardous for human beings. It's therefore crucial to carefully identify the nanoparticles that are studied. In fact, it's the classification component that works out which nanoparticles are studied. The physicists and chemists determine the physical and chemical properties of the particles, their size, shape, surface topology, and composition. They use a range of technologies based on nuclear spectroscopies of photons and electrons, allowing the creation of the most complete profile possible of the material. The analysis, studying the interaction of nanoparticles with living organisms and its consequences on human health, is carried forward through research into the in vitro toxicology, and then by the health and the pharmacology research. The aim of in vitro toxicology is to reconstitute the human tissues representing principal access points that nanoparticles would have to the human body. 3 tissue models have been developed to best represent the complexities of the human body. A differentiated epidermis, created from keratinocytes and expressing the cellular markers of differentiation comparable to those expressed in human skin. This skin is produced by Straticell, another university spin-off. A human intestinal epithelium possessing M cells and developed from the co-culture of intestinal and lymphocytic cells is used. A human bronchial epithelium prepared from bronchus cells is also used. These various in vitro models allow the testing of the impact of nanoparticles on cellular morphology, metabolism, and viability. Following on from this, the health and pharmacology research works to confirm, through animal models, the results obtained by the in vitro models. Studies of acute and subacute toxicity are carried out on animals after oral, cutaneous, and respiratory uptake of the test materials. One beneficial development has been the creation of a new technique in collaboration with the classification group, which permits the exposure of the test animals to a homogeneous aerosol of nanoparticles that reproduces exactly the same conditions that workers are exposed to. The biochemical serum, the histopathology of the various organs, the biopersistence, and the toxicokinetics of the nanoparticles are studied in the exposed animals. Finally, the ATU Science, or Wildcard Science team, works to inform the wider public through exhibitions, roundtable discussions, film debates, and via the internet. Once the project is concluded, the toxicity tests can be validated and used as reference points in studies of nanotoxicology. This would be a considerable aid for businesses that must at present supply data on health and safety as well as environmental risks for all the products they produce. This information is now required under REACH, the new European regulations for industrial chemical products.